Hello, today I want to say a few things about antennas suitable for receiving Navtex on a boat. And I want to make this as practical as possible, so I will not just be talking about antennas, I will also be testing some of them. Stay tuned. So let's have a look at some of the antennas that we will be testing today. This is the Furuno NX3H, the one that typically comes with the Furuno NX300 Navtex unit. The next one is the so-called H-vector antenna of NASA Marine. It's called H-vector because it uses the magnetic field component of the electromagnetic wave. I'll tell you more about that in a minute. Then we have the NASA Marine standard Navtex antenna. They call it Series 2. Like the two others, it's an active antenna. However, this one uses the electric field. And then I also got hold of a Furuno NX7H. That one usually ships with the NX700, the Navtex unit for professional use on SOLAS ships. It supports not only the 500 kHz band, but also the 4.2 MHz Navtex frequency. This little antenna has nothing specifically to do with Navtex as such. It's a general purpose active antenna used by radio amateurs to listen to the HF bands, anything below 30 MHz that is. It's without any doubt your cheapest option, as these antennas can be bought on Amazon for about €10. Another affordable option is this one, a simple piece of wire. For a wire of which the length is not particularly related to the wavelength of the frequency used, we call this a random wire. The one I use is just a vertical wire about 5 meters high. As we will see in a minute, for this wire you need some extra hardware to couple it to a coax cable in order to connect it to your receiver. And this is an overview of all the antenna types we are looking at. There's a few magnetic field antennas and some based on the electric field rather. From left to right, I'm showing products for the recreational boater to more professional options. And in the column at the right, I propose solutions from the world of radio amateurs. All of the antennas presented, except for the random wire antenna, are active antennas, meaning they have some kind of amplifier built into the antenna itself. Active antennas also need power to work. This power is delivered over the same coax cable that delivers the signal to the receiver. It's typically done via this kind of T-shaped circuit, also known as a bias T. The bias T allows power to be fed to the antenna while also allowing the radio signal to be sent to the receiver. The SDR Play receivers have a bias T built in, one that can provide 4.7 volts to the antenna. This allows these three antennas to work with any SDR Play receiver. The NX7H needs 9 volts for its power needs, so if you want to use that one you need a separate bias T and a 9 volt DC voltage source. Same story for the mini whip antenna, only this one requires 12 volts typically. Now let's zoom in on these magnetic field antennas. What are they exactly? How do they really work? Well, let me illustrate this through this old school AM radio. As you may have noticed, these radios can be directional, meaning there will be a point where the radio reception is gone completely when you turn them around. Inside the radio you can actually see the antenna being used here. You can see some ferrite rods on top, here with some copper coils wound around them. These rods kind of capture the magnetic field lines, making it a very effective antenna. Now let's open up this NASA Marine H-vector antenna and see what's inside. Well, inside we find indeed two ferrite antennas, two to work around the effect of the directivity and avoid the null in the antenna pattern. Other than this is a bit of a cheap design if you ask me. The way the coax is connected to the PCB doesn't look very professional. The circuit on this board is super simple, it's not shielded, and as we will see later, it has a limited frequency selectivity. I wanted to open up a Furuno antenna as well, which turned out to be a challenge in itself. I had to build a kind of tool to actually separate the top from the bottom part through some rotary motion. After a few hours of trial and error, things finally started to move and to come apart. Inside, I found a kind of shielded box built with green printed circuit board material. Removing the metal cover revealed a complex circuit with a couple of tunable elements. The actual box made out of green PCB could not be opened up any further in a non-destructive way. Luckily, the service manual of the Furuno NX700 can be found online. In there, I found a picture of the ferrite rods inside the box. In fact, there's not 2 ferrites, there's 4 of them. This has to do with the 4.2 MHz band that is also supported by this antenna. From pictures I found online, I could see that the NX3H, the antenna that comes with the NX300, is built in exactly the same way, except that it lacks support for the 4.2 MHz and therefore only has 2 ferrites instead of 4. Last thing to mention is the shielding of this green box. It has quite a few thin, horizontal copper lines on the circuit board. I wonder why it has been done this way. If anyone knows, do leave a comment. My theory is that they want to protect the circuitry inside from radar transmissions, but that's just a wild guess right now. Anyway, when trying to compare these two products just by looking at the build quality, there is a clear winner. Now you may argue that I'm comparing a consumer product with a professional product here. That is true, but even when looking at the NASA Marine product in itself, I believe this company could have done a better job in the design and build of this product. Now let's take a look at this one, the NASA Marine electric field antenna. This is really a minimalistic design. Conceptually it is comparable with the mini whip antenna. It would probably lead me too far explaining the ins and the outs of this antenna concept, but just looking at the limited number of components used, this is probably not going to be a great performer. A lot of information on the mini whip can be found online. One important element is that it needs proper grounding for achieving good results with it. The same is most probably true for the NASA Marine antenna, but I don't think NASA Marine gives any specific instructions on this aspect to its customers. They must be aware that many people have had issues trying to get this antenna to work correctly. This, by the way, is the leaflet that I found in the box of the H-vector antenna. It says this, among other things: in most small craft, the electrical system acts like an effective ground for the antenna, but it can also be a source of interference conducted from other electrical equipment on board. Electrical interference can result in poor reception, especially in a marina where the ambient level is high or at sea when poorly suppressed electrical equipment is in use. The same statement can be found on the NASA Marine website, where they even add a customer testimonial. I'm delighted with our new antenna. Our Navtex, normally somnolent in the marina, has burst into life. Let me say a few words about the random wire antenna as well. In my backyard it looks like this. There's a vertical piece of wire, or an L-shaped one like on this picture. The radio is connected via coax. There's a radiating wire and a ground connection. On a boat we can have more or less the same thing in a somewhat different way. An isolated backstay that acts as a random wire. You can find them on boats equipped with, or at least for, an HF transceiver. In that case, there's also a ground connection and an ATU, or antenna tuning unit. If your boat has this type of backstay, you could be using it as a random wire for receiving Navtex. In that case, you need to bypass the ATU for two reasons. This tuning unit is not going to tune in any way unless you transmit a signal. And even then, marine ATUs are not designed for use under 2 MHz. Now, if you aren't using an ATU, what shall you use then? What is in this blue box? Well, typically there is some kind of transformer in there to more or less match the impedance of the wire to the one of the transceiver, or in our case the receiver. You find many examples of this kind of transformer online, but there's two particular designs that are very common. Both are in fact so-called auto-transformers. That means that the primary and secondary parts of the transformer have some wiring in common. Not sure why it is often done this way. Dave Kessler, radio amateur running one of the leading amateur radio YouTube channels, says this about it.
There is a lot of tradition in there, and so people tend to do things because that's kind of the way they've always done things. Okay.
In other words, we should not be afraid to do things differently. So I built this impedance transformer with separated windings at the primary and secondary side. This avoids any corrosion risk for use on a boat. You can easily build this with simple components. The SMA terminated cable and the transformer core can be found on Amazon. I'll put links in the description. Before we look at the test results of the different antennas, there's one more topic that I would like to touch upon. Most of the antennas in the test are active antennas, so they have active components to amplify the signal. Active elements have a limited linearity. As a result of that, they can produce so-called intermodulation products. Those are frequency components that were not even presented to the antenna as such. In a worst-case scenario, these added signal components can actually distort the desired signal or even mask it completely. A way to avoid this is to apply filtering, so that out-of-band signals never even reach the active components. As we will see, the active antennas under test have a varying ability to effectively filter specifically the Navtex frequencies. Okay, the time has come to put our antennas to the test. There's just one more thing to do before we get there. We have to get rid of this TV style connector on the NASA Marine antennas and replace it by something decent. It's another one of these weird design choices of NASA Marine, using a 75 ohm cable and a connector type that is not really suitable for use in a marine environment. But okay, soldering and crimping an SMA connector is not a big deal. So let's go now and test some antennas. I'll be trying to receive a Navtex transmission using the SDR Play RSPDX. The software I'm using is SDR Connect on a Mac. Here we get a look at the spectrum below 1 MHz. We see real signals, but also some that look like intermodulation products. That's why it's certainly helping if the antenna itself has some degree of frequency selectivity. Here we are looking at what the NASA Marine electric field antenna produces. It has a limited frequency selectivity, and due to the nature of the antenna, it has a tendency to easily produce intermodulation products. Then I switch to the wire antenna. That one is also not very frequency selective as expected. On the other hand, it's a fully passive antenna, so there is no risk of intermod products generated by the antenna itself. The signal comes in weaker also in this case. Then we switch to the NASA Marine H-Vector antenna. It has the best frequency selectivity so far. However, strong, long and medium wave broadcast signals still make it to the receiver. The Navtex signal as such is quite convincing and stable. And then I switch to the Furuno NX3H. Again, a clean and convincing Navtex signal. But look at this, when I'm zooming out to show the 1 MHz spectrum. This antenna has an amazing filtering capability. You see almost no signals at all except the ones in the 500 kHz range. This is truly impressive. So I'm putting the 4 antennas tested next to each other now. I wouldn't recommend the NASA Marine E-field antenna. You see a lot of spikes in this graph, which tells us that the antenna is prone to producing intermodulation products, to the extent that receiving your Navtex signal may become impossible. In the presence of strong signals, this antenna is very likely to disappoint. The wire antenna, although not frequency selective in itself, is a good option. You may need to experiment a bit with the amount of turns in the impedance matching transformer to get a strong enough signal, and you have to make sure your ground connection is of excellent quality. The Furuno antenna is the clear winner for me. The only drawback is that it may be hard to find at a good price. You can still buy them new, and you do find them on the second-hand market as well, although not abundantly. The NASA Marine H-Vector antenna is an acceptable alternative. It's not perfect in many ways, but it does show good results in this small test, and its price is acceptable. The only thing left to do now is to see a Navtex receiver system working on an actual boat.
Welcome in Belgium on a rainy day, on a boat obviously, and the Navtex antenna, the Furuno NX3X, is now installed on the boat. I'm quite happy with the installation. I was able to hide the cables in this metal structure. I'm a bit disappointed by its performance though. It's not working as good as I was hoping to. I received some messages, but here in Belgium I should be receiving messages from the Netherlands, the UK, Ostende obviously, France as well. But I hardly get some messages from Belgium if I'm lucky, and I get some errors occasionally. So it's not yet working the way I want to, so I have some troubleshooting to do.
And in fact, the culprit turned out to be closer than I could imagine at that moment. Some time ago I revamped this GPS antenna from an old analog type to a unit that produces NMEA information that is sent to the instruments on the boat via an NMEA multiplexer. I made this using these cheap components from AliExpress and Amazon. This is what I actually received from the Furuno antenna installed on the boat. And this is what happens when I switch on the power to the GPS antenna. Clearly this GPS antenna has become a huge source of noise. The DC-DC converter that I'm using to feed 3 volt to the GPS module is the prime suspect here. The high-speed switching going on within the converter is the root cause, most probably. I should have known better. When trying to receive Navtex messages with the GPS antenna switched off, the system behaves exactly the way it should. I'm receiving messages not just from Belgium, but also from all the Navtex transmitters whose theoretical coverage area I'm in. There's messages from the UK, but also from Germany, and this one from France. I love it when a plan comes together.